So let's continue our discussion on magnetic dipole moments, and let's determine the magnetic dipole moment of an electron orbiting a single proton, as in the case of the hydrogen atom. So this is our Bohr's depiction of the hydrogen atom. We have a single proton in a nucleus. The neutron is omitted because it has no electric charge. And this is our single electron that is orbiting our proton via the following circular pathway. So what is the magnetic dipole moment mu of the electron that is orbiting our nucleus? Assume the radius of this pathway, the radius of this orbit, is 5.29 times 10 to the negative 11 meters. So to calculate the magnetic dipole moment mu, we simply have to take the product of the electric current I and our area of this orbit A. So let's begin by calculating what the electric current is. To calculate the electric current, we have to calculate the velocity. So let's begin by applying Newton's second law of motion. So according to Newton's second law of motion, the net force acting on our electron in orbit is equal to the mass of that electron multiplied by the acceleration. Now the only force acting on our electron is our electric force, which is equal to K, the constant, multiplied by Q1, the charge of the proton, multiplied by Q2, the charge of the electron, divided by the square of our radius r, the distance between these two electric charges. And that is equal to the mass of the electron multiplied by the centripetal acceleration of the electron in orbit. So V squared divided by r. So we take this equation and solve for the v, and the velocity is equal to the square root of k, our constant, multiplied by q1 multiplied by q2. So the square of our charge, because the quantity of charge on these two charges is exactly the same, divided by the mass of the electron multiplied by the radius. So we plug those values into our calculator, and we see that the velocity, or the magnitude of velocity of the electron in orbit, is equal to 2.19 times 10 to the 6 meters per second. So now we can use this velocity to calculate what the I is. Recall that our electric current around this orbit, around this pathway, is simply equal to the quantity of charge that passes one full revolution divided by the time it takes our electron to travel that revolution. So I is equal to the charge divided by the time. Now the charge is equal to the charge on one electron, and our time is simply the period of our orbit. The period is simply equal to the circumference, the distance traveled by the electron, divided by the velocity of that electron. So the Q is simply the quantity of charge on one electron, and the period t is equal to 2 pi r, our circumference, divided by our velocity. Now we know what the velocity is, we know what E and R is, so that means we can solve for our I. So we take this, we bring it on top, and we solve for I, and we see that E times V is this, divided by 2 pi times the radius, which gives us 0.00105 amps. This is our electric current around the following circular pathway. So now we calculate what the A is. What exactly is the area of this circular orbit? Well, it's essentially pi multiplied by the square of the radius. So the area of the orbit is equal to 2 pi r squared, is equal to pi multiplied by the square of the radius, which is equal to about 8.79 times 10 to the negative 21 meters squared. That's the area of this orbit made by our electron as depicted by Bohr's model. Finally, we apply this equation. The mu, our magnetic dipole moment of our electron as it orbits this single proton, is equal to I multiplied by our A, and that gives us about 9.23 times 10 to negative 24 amps multiplied by meters squared.